Resolving P versus NP requires navigating obstacles in infinite dimensions. To analyze them precisely, we compress these barriers into a finite combinatorial space. This lean code block represents a mechanized proof of that compression. It is a single theorem containing 4 logical clauses, each proving that a different known barrier to a P versus NP solution exists within this 4-bit universe. In standard complexity theory, these structural walls operate on infinite domains, making them abstract and difficult to pin down with mechanical certainty. The strategy here is to restrict the entire computational universe to a maximum of 4 bits. By shrinking the scale, we create exact combinatorial shadows, finitary versions of the barriers, exhaustively verified by a computer. The proof closes with native decide, meaning the system verified every possible permutation in this 4-bit universe using purely mechanical brute force. The theorem succeeds only as all 4 clauses, connected by logical ands, are verified true. To understand why P versus NP remains inexpressible, we have to deconstruct what each of these 4 clauses represents within our 4-bit sandbox. Together, they demonstrate that the friction of NP hardness is woven into the logic of even the smallest possible computational systems. We begin by defining the time hierarchy shadow. This measures the baseline of computational effort required to evaluate an instance. In this universe, a program tasked with deciding a language based on 3 bits of input will fail if it only inspects the first 2. It is a physical limit. You cannot determine the state of the 3rd bit without looking at it. Next, we introduce the Cook-Levin shadow. We take a specific Boolean formula, a 3CNF, operating on 4 variables. In a 4-bit universe, there are exactly 16 possible assignments. Our specific formula has exactly 8 satisfying assignments, where the logic evaluates to true. Using the Karp reduction shadow, we can translate this logic problem into a geometric one. Each piece of the logic formula is converted into a distinct vertex on a graph, 12 vertices in total, organized into clusters. Edges are drawn between these vertices, but only if they represent compatible literals in different clauses. Finding a valid solution to the logic formula is now mathematically identical to finding a forkleek, a fully connected subgraph within this web. This establishes our baseline. Structural NP hardness exists even at 4 bits, requiring a machine to inspect global states rather than isolated local ones. Many mathematical techniques are relativizing, meaning they work the same way even if the algorithms are given access to a black box oracle. The problem is that these black boxes can answer queries instantly, creating different scenarios for how P and NP interact. We can model this in a strict 2-bit universe using 2 different oracles. Oracle A is trivial. It answers true to every query it receives. Under Oracle A, a deterministic decider reading 1 bit and a non-deterministic decider guessing 2 bits are in perfect agreement. In this specific world, P and NP are entirely indistinguishable. Now we switch to Oracle B. This box only outputs true for one specific sequence, 2 true bits. The deterministic decider fails because it cannot see the full sequence with its limited reads. It cannot exhaust the search space, while the non-deterministic decider correctly guesses the full certificate and succeeds. This creates a contradiction. In one world, P and NP are the same. In the other, they are different. Any proof technique that treats computation as a black box will fail to separate P and NP, because it would have to be true in both of these conflicting realities. Another obstacle involves broad mathematical properties used to categorize functions. If a property is too broad, it captures more than just the complexity it seeks. This is the natural proofs barrier. It limits our ability to separate complexity classes by using general properties of Boolean functions. We test this using functions on 3 bits, represented by 8-value truth tables. A property is considered natural if it labels a large fraction of all functions and can be verified simply by inspecting the truth table. Our test property, prop_large, requires a truth table to have at least 2 true entries to pass. This property is indeed large, passing more than a quarter of the 256 possible functions in our universe. The property correctly identifies a random-like parity function, giving it a yes. The same gate then evaluates a highly structured small circuit function. Because it also contains at least 2 true entries, the property labels it as a yes as well. The property fails as a separator. It cannot mathematically distinguish between the complex randomness it seeks and a simple, compact circuit. We return to the master lean theorem. It binds these 4 separate shadows into a single verified state. It proves that the translation from logic to graphs is consistent at 4 bits. It demonstrates the relativization collapse and separation using oracles A and B, and it confirms the inability of natural properties to act as a clear filter. Because this universe is finite, the native decide command has checked every possible state. There are no edge cases left unexamined. These results suggest computational hardness is not just a feature of massive datasets, but a structural friction present in the basic logic. Any proof attempting to resolve P versus NP must account for all of these barriers simultaneously. For now, they form a coordinated wall that known mathematical methods have yet to bypass.